Hi, we are group number 51, and our project title is Bear the Query in Mind, Visual Grounding with Query-Aware Dynamic Convolution. Before we start, let's play a game. Please memorize the image and be prepared to answer a question. Ready? Now please tell me, where is the man wearing glasses? Is he on the left or on the right? It is hard, right? Let's play it again. This time, I present to you both the image and the question. The game becomes much easier, right? Because you know what to look for in advance. The game we played is called visual grounding. To define it in machine learning, given a query image pair, the machine needs to predict the coordinates of the bounding box of the target object. Similar to showing you the image and asking the questions later, most previous approaches in visual grounding are doing the same thing to their models. They encode image and text separately and then perform fusion with another module, such as cross-attention, at the end. This requires the visual encoder to memorize the entire image with equal attention on all the details, as they don't know what exactly to look for. This may lead to incorrect and fuzzy focus when they see the query in the Fusion module. The correct thing to do is to show you the image and query at the same time. This gives rise to our proposed method naturally. We add the query information into convolution kernels in the vision encoder so that our vision model knows what to search for in the image in advance. In this case, the vision encoder can extract query-aware features, and we also eliminate the need for a Fusion module. Here is how we incorporate query information into vision encoder. The basic idea is to construct convolution kernels according to different queries. First, we create k candidate kernels with the same size, and then use a weighted sum to generate the dynamic kernel, which we later use as a usual kernel in ResNet or other CNN backbones. The query information is embedded in attention weights pi1 to pi k. Intuitively, each candidate kernel is able to detect some features, and we let the text query to control which features to detect by letting it assign weights to candidate kernels. The weight assignment is treated as a regression problem. We first get the sentence embedding for the query with BERT. Then we use nonlinear projections with the softmax layer to output the weights. As we train the model end to end, these projections will be able to learn the correct weight assignment according to text query. We use TransVG as our baseline, and here are the two structures with dynamic convolution we have tested on. We first successfully reproduced the original TransVG. In the first variation, we replaced the convolution layers in the ResNet backbone with our query-aware dynamic convolution block. In the second variation, we further removed the Fusion module by attaching a reg token to the visual transformer and using it for coordinates prediction. We use RefCoco dataset in our experiments. Here is our experiment result. We can see that, first, dynamic convolutions can improve the performance of the baseline by 2.3%. Second, after removing the Fusion module and solely relying on dynamic convolutions to incorporate text information, the model can achieve the same level of performance as TransVG. Thirdly, according to empirical results, dynamic convolution is actually faster during inference. To investigate how query-aware dynamic convolution improves the accuracy, we first visualize the attention in the transformers. We can see that the attention in our dynamic convolution models is more focused and plot a tighter boundary around the target. It locates the correct features in layer 1 to 3 and expands to finding the bounding box coordinates from layer 4 to 6. However, in the original TransVG, several features have equal attention in the front layers, so later it may focus on the wrong feature and expand attention range and get a fuzzy boundary. Then, we look into the attention weight and convolution kernels in every dynamic convolution block. We plot the attention weights of the 20 dynamic convolution blocks, and each has 5 candidate kernels. We find that in the first 15 attention weights, the attention distributes are generally even, and the activation of a particular attention weight represents special text information. For example, the last attention weight in block number 6 is activated when queries contain the word blue, and the last attention weight in block number 10 is activated when queries contain the word red. In addition, to eliminate the impact of image, we use the same image with different queries to visualize the attention weights, and we also find that queries with similar semantic meanings can produce similar attention patterns. For example, the left 2 queries describing woman look similar, and the right 3 queries describing the man look similar. This proves that our attention weights effectively encodes text information. We further looked into the dynamic convolution kernels and found that they did capture text information in a similar way as text embeddings. We calculate the cosine distances between the dynamic kernels of different queries. For queries with different semantic meanings, the cosine distance of their dynamic kernel weights will be large. For queries with similar semantic meanings, the distance between their dynamic kernel weights will be very small. This proves that the aggregated dynamic convolution kernels embed meaningful textual information. This distance relationship holds regardless of the particular information represented by attention weights and candidate kernels. To conclude, in this presentation, we introduced a query-aware dynamic convolution architecture for visual grounding. It improves upon the baseline model without following the conventional extract and fuse methods. It also increases inference efficiency and model interpretability. We also analyzed the behavior of dynamic kernels and its impact. In the future, we could try different ways to incorporate query into vision. We could apply our idea to more multimodal tasks involving more modalities such as audio and video. Thanks for watching. I hope you find our idea interesting.